Welcome to Math Minecraft Computers episode I-7, Introduction to Logic Gates. Today we're going to talk about logic gates. And logic gates are a very basic component that we use to build computers. Now it's actually pretty simple on how they work. I'm going to first start by saying that I use, for any gate, a different color block. My block of choice is the green terracotta. I guess it reminds me a little bit of the old circuit boards, and the white a little bit of the old breadboards. I've built a couple of breadboard computers, so I kind of like the combination. As we talked about in the past, there's different things we need to build circuits. First is a way to transmit a signal, which in this case is our redstone wire. Then we need an input or that signal, which can be anything from a redstone torch, or it could be a switch or anything like that. I'm going to go with a switch here and I'll turn that on. And then of course, we need some sort of output or load at the end, which is going to be, in this case, a redstone lamp. These are really all you need to build a computer with one other component. And that component we've already talked about. We've used it to invert a signal. So if I come here and I put down a block and I put a torch on the side of that block like this, then what I'd get is an inverted signal. I'll come out here and I'll put my redstone lamp there. So now when this switch is off or on, the state changes. So when it's off, the lamp is on because this inverts the signal from here, off to on there. Of course, when I turn this on, then I get it inverted. And really, this is all you need to build any kind of circuit. I'll show you one thing you can do pretty quickly. I'll get rid of these. I'm going to build two of those gates. Now, the first gate is called a NOT gate, and a NOT gate is exactly what I talked about. It simply inverts the signal. So, going here, I'll build this construct. That is a NOT gate. It's a block with a torch on the side. The input comes in over here. I'm going to build another one of these real quick. I'm going to put it here. And then I'll run some wire out this way. And eventually we'll go into a light right here. Obviously, in either case, as I turn these off, those will come on. So you'll see something interesting occur here. When they're both off, then I get a signal over here. As soon as I turn one of these on, you'll see the signal back there dies. It's the same thing that occurs here, just like this. So if I were to do something a little bit different and take these two, and to put them actually into a block, which I'll put over here for simplicity, I'm going to run this one into there as well, and then put a torch on it to invert the signal. One chunk of wire, and I think we'll elevate this one just to make it. Now I use the white concrete, that's my choice for my base here, to do elevations and things that are not actually part. So the only thing that is green would actually be the gates themselves. So in this case, I'll run the wire up here and I will put the light there. If I come back here and I turn these off, you'll see that the light is off. If I turn one on, the light stays off. Turn this one on, light stays off. So only if they are both on do I get that on. This is actually our second type of gate. This is called an AND gate. It's called an AND gate because it says this input and that input must both be on. One on doesn't work, only two. So if this one and this one are both on, then my output is on as well. If either is on, like this, or they are both off, then I don't get an output, and our last combination is here. Off, off means output of off. On, off, same thing. Off, on, so here's my off, there's the on, I still get an output, and then of course on, I get them on. So this is actually what we do to build an AND gate. It takes three NOT gates. One here, they both feed into a third NOT gate. We can do this a lot simpler in Minecraft. You'll see it more in this form. Put down three blocks like so. Put a torch up on top here. Put a torch up on top here. And then we have redstone wire. These would be our inputs. I'll put down the switches. And then we connect these two with some redstone wire. Put a torch down here. And finally our output, and I'll put it to this block. Now if you can see, there I had a NOT, two NOT gates here, feeding into another NOT gate. And we basically have the same thing here. So here's the NOT gate. The second side over here is also a NOT gate. And then those two are connected here to lead to this third NOT gate. So now I'll get this exact same thing. They're both off. The output is off. Turn either one on. The output is off. Turn them both on. I get it on. So this is an AND gate. The logic is to say, do I have more than one input? And it is only on. The output of the gate is on only if both or and this. Now you can do multiple as well. So this is a 2-input AND gate, but we can also have a multi-input AND gate, in which case I'll just do 3. But these can be as big as you want them. Actually, I need to do it here, and then I'll put my third one here. So these are the 3 inputs. In this case, we put torches on the inputs. We run wire, and the reason I use wire is, we'll see in a little bit when I get to the OR gate. You could just put the switch right here. That works, of course, because I just got to have power to that block. But there is a reason not to do that. You want to make sure when you're designing and building your gates that you have inputs separate. Now we just run wire all across these so they're all connected. Just like this. And then we have to put our last NOT gate here, and then we'll turn this on. So now what I have with this is 3. Now I have 3. Over here I had a simple 2, 1, and 2. That could be 2 bits, bit 0, bit 1. Here I have bit 0, bit 1, and bit 2. So now when I turn these on, turning any one on does not turn on the gate, and so the light stays out. Turning any 2 on is the same. The only way to turn it on is all 3. And say when they're all 3, you see that indeed the other side is powered, and therefore we have an output. So that's a multi-input gate. These can be as big as you want them to be. That is kind of unique to Minecraft, not in electronics. There's the AND gate. There's the multi-input AND gate. Can be as big as you would like. Moving on to the OR gate. The OR gate is very simple. It is another logic. Now, you can just lay down redstone wire. Let's say this is one input. This will be the other input. And we want maybe this light to go in right here. Well, it's pretty simple. Here we go. I've got this on. So in this case, it's either or both. So if either input or any one input is on, this input here or that input there, then we want the circuit on. So that's an OR gate. But one of the issues you have with this particular problem is, as you can see, you might have another circuit that leads into here or away from here. And you don't want it powered when you turn this one on. But you can see it's going to power it all the way over here. Very often when you're doing an OR gate, you'll find it. Now the way I would still do this, even if I were doing this, is I would put down my green block here to denote that this is a gate of some sort of logic, like this. I still have that problem of this side turning on this other side. So maybe a question or a way to solve that is I'm going to put this, I only want that on if this switch is on. I do not want it on when this switch is on, but you can see that it turns on. What are we going to do? And you guessed it, we're going to replace this with a repeater right there. Remember, a repeater acts as a diode. Also, power can only flow in one direction. It flows in this direction. It cannot flow in this direction. So when I turn this on, and this, I have the same thing. So exactly what I wanted. Now this works, as you recall, because this strongly powers this block, which could be a problem if you're not careful, because you may not want that powered. If I try to run redstone out of that block, it is powered even this way. So when you're doing that, keep in mind that you're strongly powering that block. If you didn't want that block strongly powered, then of course you would just have to put your repeater somewhere else, such as, in this case, you wouldn't be able to connect here. If you put your power in any place here, that repeater needs to be in this direction. So I ended up adding wire. I had to put my repeater in front of here, and something like this, let's say. So I would bring this connection over here. I would have to put a repeater right there, and then my switch would be here. And now we accomplish the same thing. Now we have the OR gate, which is either or both. We also want a gate called an exclusive OR, where I only want if one or the other. So this would light it, but it would be turned off in that case. So we'll add a couple of switches here. And these will be our inputs. I'll run those. And the way this is created is we need two NOT gates, a NOT here. Those are going to be connected together with wire and run into a third NOT gate right here. Then we're going to take the output of that gate. It's going to be the input, so it's going to come in over here like this. We do the same thing from here. And then the last thing that we're going to do is bring these two outputs here into yet two more NOT gates, here and here. And we combine those, and we put our output there. In this case, when they're both off, the input is off. When I flip one, when they're both off, when they're both off, the output is off. When I flip one, it comes on, or the other, but when they're both on, it goes off. So this is an exclusive OR gate. It means exclusively OR, not both, one or the other. Off, it's going to be on, and if they're both on, it goes off. That's an XOR gate. Once again, if you remember, this is basically an AND gate, as we build an AND gate over here, so this can be done differently. To build the XOR gate simplified, then we need to start with the AND gate, which we've already seen how to build. Do it just like this. These are going to be our inputs. In this case, there they are. And normally we put a torch down here for an AND gate like this. Got that, completely missed that, so let me try that again. Here, put a torch here, and we have wire across the top. That's an AND gate. What we're going to do is we're going to put another block here, run redstone wire to it with a torch here, one on the side there, one on the side there. Now we need to bring these out from here, and then we put another block in front of those, like this, with torches here and here, redstone here, the redstone here, and then finally these two are of course tied together, and the output of our block is. So this should be exactly the same as this. Here we built it strictly with NOT gates. You can see back there we end up having what is equivalent to an AND gate, and then here's the two NOT gates. So here we have that all construct right there, and then the two NOT gates on the end. So it's just a little shorter, simplified, still works. There it's off. Turn any one on, it comes on. Turn them both on, it goes off. So that is an XOR gate. All right, now we're going to talk about what is called a truth table very quickly. So in this case, if I go to my AND gate, which is very quick to build, this solves a problem in logic that we have two inputs here, and we have a single output. Now, if you think of our inputs as ones and zeros, what this is going to solve is this problem. If I have my two inputs of 0, I'm going to get a 0 out. If I have a 1 and a 0 this way, I still have a 0. If I do a 1 and a 0 in this manner, I still have a 0. Only if they're both 1 do I get a 1. That's exactly what this does. So 0, 0 equals 0. Turn this one on, it's not on. Turn this one on, it's not on. And eventually we get it right. So that is what an AND gate does. Put it on the side and say AND. An OR gate, as we built it before, very simple. Connect it here, connect it here. I'm not going to put in the repeater to stop the power. Go with the switch. There we go. And then we have an output that comes out of here. In this case, it has this sort. 0, 0 equals 0. 0, 1 equals 1. 1, 0 equals 1. And of course 1, 1 equals 1. This is what this outputs. Anytime there's any single 1 in the system, then we get it and exactly what it is. There's 0, 0, 0, 1, 1, 0, and 1, 1. And you can see we get the output. Now the XOR gate that we built over here has this sort. So if it's 0, 0, it's 0. If it's 0, 1, we want it 1 out. If it's 1, 0, we want a 1 out. And of course, if it's 1, 1, we want a 0 out. So we go through those, we'll turn both off. You can see it's off as well. Turn this one on, that's the second line down, 0, 1, we get a 1. Turn this one on, that one off, that's the third line, we get a 1. And of course, if they're both on, we get a 0. So this is an XOR. Now the only other gate that we're going to use most of the time, that would be a rare situation, is called a NAND gate. And you build it just like an AND gate. We need a redstone here, here, and here. And there are 2 inputs. Now instead of putting a torch down here, we simply have our output coming like so. Now you can see it's on with both of these on. Let's flip these around. Okay, when they're both on, the gate is off. If any switch is on, it's on, and if they're both off, it's on. So the output of the NAND gate is negated AND. So as you can see, any combination but this one, the light comes on. So its table looks like this. 0, 0, we get a 1 out. 0, 1, we get a 1 out. 1, 0, we get a 1 out. And only if we get 1, 1, 2, we get a 0. And so let's look at that. 0, 0, it's on. 0, 1, it's still on. 1, 0, 1, it's on. And 1, 1, it goes off. This is called the NAND gate. A negated AND. Like so. And if you look at the opposite between it and the AND gate, you'll see it's exactly the opposite. 0, 0, 0, 1. And then down here you have 1, 1, 1, 0. So you can see that's the opposite. 0, 0, 0, 1, 1, 1, 1, 0, because the difference is we did not negate. So those are our logic gates, starting with the very simple OR gate, where we take 2 together here. We have the AND gate, where we have only if both inputs are on, is it on. We have the XOR gate here, which is only if one or the other is on. And then lastly, we have the NAND gate, which is the opposite of an AND gate. Only are off if both inputs are on. So those are the gates we have. By using these gates and combining them, we can do all kinds of logic. That is called combinatorial logic, because we're going to combine various gates. In most cases, it will only be AND, ORs, and XORs. This gate is a universal. You can actually use it to build all other gates, which we'll get to later. Right now, we're going to stick with the more simple AND, OR, and XOR. So it's these 3, the AND, the OR, and the XOR. Various projects.